All right, this is Unit 6, Lesson 7, Geometric Sequences and Series. Our lesson essential question is, how can you represent and use geometric sequences and series? At the end of this lesson, you'll be able to identify, write, and use geometric sequences and series. All right, example 1, identify geometric sequences. A, is the sequence shown in the table a geometric sequence? If so, write a recursive definition for the sequence. So way back a couple of chapters ago, we talked about arithmetic sequences. So these are geometric. So arithmetic, we added or we subtracted. For geometric, we're going to be multiplying or dividing by the same number. Okay? So term number n, 1, 2, 3, 4, and 5. Our term is 4, 12, 36, 108, and 324. So from here to 12, I would have multiplied by 3. 12 to 3, I multiplied by 36. And we continue, okay? So a geometric sequence is a sequence with a constant ratio between consecutive terms. This ratio is called the common ratio R. Notice the relationship between the terms in this sequence. Each term is 3 times the preceding term. So this sequence is a geometric sequence, since for n equals 1, a sub 1 equals 4, r equals 3, and a sub 2 equals a sub 1 times 3. So a sub 3 equals a sub 2 times 3, a sub n equals a sub n minus 1 times 3. So the recursive definition for this sequence is a sub n equals 4, where n equals 1, and 3 times a sub n minus 1 when n is greater than 1. 4 is the first term, n is the term number, 3 is the common ratio, and the preceding term, a to the n minus 1, multiplied by the common ratio, is the next term in the sequence, a sub n. So the general recursive definition for a geometric sequence is a sub n equals 4, when n equals 1, and r times a sub n minus 1, when n is greater than 1. B, is the sequence 12, 9.6, 7.68, 6.144 a geometric sequence? If so, write the recursive definition for the sequence. So I find the ratio between the consecutive terms. So 9.6 divided by 12 equals 0.8. 7.68 divided by 9.6 equals 8.0 or 0.80. And 6.144 divided by 7.68 gives me 0.80. So that means I'm multiplying by 0.80 each time. So the ratio between the consecutive terms is constant. So it is a geometric sequence with a sub 1 equals 12 and r equals 8. So the recursive definition for the sequence is 12 when n equals 1 and 0.8 times a sub n minus 1 when n is greater than 1. All right, so let's try it. Is the sequence a geometric sequence? If so, write a recursive definition. 1.2, 1.45, 1.68, and 1.91. So the first thing that I want to do is I actually want to divide 1.45 by 1.22. And I get 1.18. I'm going to do the same thing with 1.68 and 1.45. Okay. So 1.45 divided by 1.22 equals 1.188. 1.68 divided by 1.45 equals 1.15. So there is not a common difference. So this is not a geometric sequence. For B, I have negative 1.5, 0.75, negative 0.375, 0.1875. Okay, so I know that I'm going from a negative to a positive, from a positive to a negative, negative to positive. So I'm going to be multiplying by a negative number because a negative times a negative gives me a positive, positive times a negative gives me a negative. So I know if this is a geometric sequence, I'm multiplying by a negative number. Okay, I'm going to do the same thing that I just did, 0.75 divided by negative 1.5, which gives me negative 0.5. Okay. And I take negative 0.375 divided by 0.75. also gives me negative 0.5. I'm going to double check the last one, 0.875 divided by 0.375. Also gives me negative 0.5. So that means my R is negative 0.5 or negative 0.5 or negative 1/2, however you want to write it. So my recursive definition is going to be A sub n equals negative 1.5 because that's my first term, if n equals 1, and then A sub n minus 1 times negative 0.5 if n is greater than 1. Right, example 2, translate between recursive and explicit definitions. So given the recursive definition, A sub n equals 5, n equals 1, 1/2 times A sub n minus 1, where n is greater than 1, what is the explicit definition for the geometric sequence? Okay, so the first term is 5, and the common ratio, R, is 1/2. The recursive definition is A sub n equals 1/2 A to the n minus 1. Use this definition to find a pattern. So A sub 1 equals 5. A sub 2 equals 5 to the 1/2, 5 times 1/2. A sub 3 is 5 times 1/2 times 1/2, or 5 times 1/2 squared. Then I multiply by 1/2 to get 5 times 1/2 cubed. So the pattern reveals the explicit definition for the sequence A sub n equals 5 times 1/2 raised to the n to the 1 power. So in general, the explicit definition for any geometric sequence is A sub n equals A sub 1 times R raised to the n minus 1 power. So I start with my first term, I multiply it by my rate, and I raise it to the power of n minus 1. All right, so given the explicit definition, A sub n equals 3 times 2 to the n minus 1, what is the recursive definition for the geometric sequence? So from the explicit definition, A sub 1 equals 3, R equals 2. The recursive definition for the sequence is A sub n equals 3 when n equals 1, and 2 times A sub n minus 1 when n is greater than 1. So 2, that was my rate, times A to the n minus 1. All right, let's try it. Given the recursive definition, A sub n equals 12 when n equals 1, and 1/3 times A sub n minus 1 when n is greater than 1, what is the explicit definition for the sequence? Okay, so my explicit definition for the sequence is going to be A sub n equals my first term, 12, times my rate, my R value, raised to the n minus 1 power. All right. B, given the explicit definition, what's the recursive definition? So my recursive definition equals 6 equals 1, and then 1.2 times A to the n minus 1 when n is greater than 1. Example 3, solve problems with geometric sequences. So a phone tree is when one person calls a certain number of people, then those people each call the same number of people, and so on. So like if I called 2 people and each of those people called 2 more people. Okay, so if we're looking at it, one person calls 3 people, that person calls 3 people, each of those people call 3 more people. So in the 5th round of calls, 243 people were called. Write an explicit definition to find the number of people called in each round. So A sub 1 equals 3 and A sub 5 equals 243. Okay, so A sub 1, this person called 3 people. The first person called 3 people. Okay, I can write the general explicit formula. A sub n equals A sub 1 R to the n minus 1. 243 is my A sub n, my A to the 5th. equals 3 times r, 3 was my first one, r to the n minus 1. Okay. I'm going to isolate. I substitute in 5 for n because a sub 5 equals 243. So I have 243 equals 3r to the 4th power. I want to get the power by itself. So I isolate it, which means I divide both sides by 3 to get 81 equals r to the 4th. Okay. Then I solve, disregard any negative solution. So r to the 4th equals 81. So 3 to the 4th equals 81. So r equals 3. So the explicit definition is a sub n equals 3 times 3 to the n minus 1. How many people were called in the 8th round? I use the explicit definition and solve for n equals 1. So a sub r equals a sub 1, where r is n minus 1. We want to figure out where the 8th round was. So a sub 8 equals 3 times 3, 8 minus 1. So that's 3 to the 7th power. So 3 to the 7 times 3 is 6,561 people. So in the 8th round, 6,561 people were called. All right, let's try it. A geometric sequence can be used to describe the growth of bacteria in an experiment. On the first day of the experiment, there were 9 bacteria in the petri dish. On the 10th day, there were 3 to the 20th bacteria in the dish. How many bacteria were in the dish on the 7th day of the experiment? So I can recognize that a sub 1 equals 9, okay? But I know that I'm dealing with an exponent right now. So I want to see if I can rewrite 9 using an exponent. I can, which is 3 squared, okay? So on the first day of the experiment, I have 3 squared bacteria, okay? On the 10th day, or a sub 10, I have 3 to the 20th. So now when I solve this, okay, so I have a to the n equals r to the a sub 1, r to the n minus 1 power. Okay, so if I have 3 to the 20th equals 3 squared times r to the 9th, 3 to the 20th divided by 3 squared. So I have 3 to the 20th divided by equals r to the 9th. Okay. So 20 divided 3 to the 20th power divided by 3 to the 3 squared power gives me, they have the same value base-wise, so I can subtract their exponents. So 20 minus 2 is 18, so 3 to the 18th power equals r to the 9th. 3 to the 18th, I can recognize as 3 squared to the 18th power, or 3 squared to the 9th power equals r to the 9th. So r equals 3 squared. And then on the 7th day, a sub 7 equals a sub 1. A sub 1 times r to the n minus 1. So a sub 7 equals 3 squared. My rate, which is 3 squared, raised to the n minus 1 power, or the 6th power. Okay, so a sub 7 equals 3 squared. 3 squared to the 6th power is 3 to the 12th power. Okay. And then since these both have the same base, I get 3 to the 14th. All right, example 4, formula for the sum of a finite geometric series. How can you find the sum of a finite geometric series? So a geometric series is the sum of the terms of a geometric sequence. So S sub n represents the sum of the geometric sequence with n terms. So I write the equation for a geometric series. So S sub n equals a sub 1 plus a sub 1 times r plus a sub 1 times r squared, blah, 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 keeps going. Okay. So r times s sub n equals a sub 1r plus a sub 1r squared plus a sub 1r cubed, so on and so forth. I multiply each side by r, then I subtract the second equation from the first equation. So this minus this. So I get s sub n minus r sub n equals a sub 1 minus a sub 1r to the nth power. I factor out. On this side, I factor out an s sub n, and on the right-hand side, I factor out an a sub 1. So I get s sub n times 1 minus r equals a sub 1 times 1 minus r to the nth power. I solve for s sub n, so I get a sub 1 times 1 minus r to the nth divided by 1 over r, where r, of course, cannot be 1 because that would make it 0, and bad things happen when you divide by 0. So this is my formula. So I want to write the expanded form of the series n equals 1 to 7, 3 times 2/3 to the n minus 1. What is the sum? Recall how to use sigma notation to represent a series. So in this case, my sigma notation tells me that I'm going from 1 to an n value. So a sub 1 r to the n minus 1 equals a sub 1 plus a sub 1 r plus a sub 1 r squared plus a sub 1 r cubed plus all the way to a sub 1 r to the n minus 1 equals a sub 1 times 1 minus r to the nth divided by 1 minus r. Okay. So the series is 3 plus 2 plus 4/3 plus 8/9 plus 16/27 plus 32 over 81 plus 64 over 243. To find the sum, use the sum of a finite geometric series formula with a sub 1 equals 3, r equals 2/3, and r equals 3. Okay. So r equals s sub 7 equals 3, my first term, times 1 minus 2/3 to the 7th power, 2/3 my r value, divided by 1 minus 2/3 equals 2059 over 243. I can, of course, double check by finding the sum of the terms directly. 3 plus blah, blah, blah gives me the same answer. So I want to write the expanded form of the series, the sum of n equals 1 to 5, 1/2, 3, n minus 1. What is the sum? Okay. So again, my formula is s sub n equals a sub 1 times 1 minus r to the nth divided by 1 minus r. Okay. In this case, I'm looking for s of 5. My a sub 1 equals 1/2, and my r equals 3. Okay. So I'm looking for a sub 5, so that's going to equal my a sub 1 value, or 1/2, times 1 minus my rate, my r, which is 3 raised to the 5th power, because it's a to the n minus 1, or 4th power. No, 5th power. Okay. Okay. And this is all over 1 minus r, which is 3. When I do all these calculations, I get 121 over 2. That's my sum. I'm writing the expanded form. So my first term is 1/2. My next term is 3/2. So for 1, 3, remember this is my first term anyway. So then I multiply that number by 3 to whatever power it is. So if it's the second term, I do 3 times 1/2. The third term would be 3 squared, which is 9 times 1/2, so plus 9/2 plus 27/2 plus 81/2. This is all going to be 121/2. Next, I want to write the series -2 plus -2/3 plus to -2/243 using sigma notation and find out what the sum is. So my first term, my a sub 1 equals 2. My r is 1/3. -2 times 1/3 gives me -2/3. Okay. So then I need to figure out what this number is, so what my n value is. So my last one is -2/243 equals -2 times 1/3 raised to the n minus 1 power. I'm going to divide both sides by -2. -2 divided by 243. Divide that by 2. This gives me -1/243. 1/3 n minus 1 sides. Take log of -1/243 equals the log of 1/3 n minus 1. I can bring that down. Gives me 5. 5 plus 1, 6. So excuse me, 5 plus 1, 6. You can't take the log of a negative number. So that's my n value, so n equals 6. I need to figure out that so I can figure out my sigma notation. All right, so now sigma notation is going to give me n equals 1 to 6, or -2 times 1/3 to the n minus 1. Okay. And then my solution to that is going to be a sub 1 equals -2, a sub 6 equals -243, 2/243, r equals 1/3. And then s sub n equals a sub 1 times 1 minus r to the nth divided by 1 minus r. So this is going to give me -2 s sub 6, -2 times 1 minus 1/3 to the 6th power divided by 1 minus 1/3. And let's see, -2 times 1 minus 1/3 to the 6th power divided by 1 minus 1/3, which gives me -728/243. All right, example 5, number of terms in a finite geometric series. How many terms are in the geometric series 200 plus 300 plus 450 plus up to 7,688.7. So since the series is geometric, you can find that r equals 1.5. Use the explicit definition to find n, the number of terms. Okay, so 7,688.7 equals 200 times 1.5 to n minus 1. I substitute the last term in the series into the explicit definition to determine n. Divide both sides by 200. Take the log of both sides. Remember, I can bring the n minus 1 down front, the power property. So I get log 38.4435 divided by log 1.5, and then I'm going to add 1 to that. So it's approximately 10. So there are 10 terms in the geometric series. So the sum of a geometric series is 11,718. The first term of the series is 3, and its common ratio is 5. How many terms are in the series? So again, I'm going to start with this definition, the substitute for S sub n, A sub 1, and R in the formula for the sum of the geometric series to find n. So I get 11,718 equals 3 times 1 minus 5 to the n divided by 1 minus 5. I simplify. Divide both sides by 3. Subtract 1 from both sides. Or I just flip some stuff around. I'm adding. Okay. Once you've isolated the term with the exponent, take the log of both sides. So log 5 to the n, which becomes n log 5 equals log 15,625. Divide both sides by log 5, and n equals 6. So there are 6 terms in the series. All right, so let's try. How many terms are in the geometric series 3 plus 6 plus 12 plus up to 768? So I want to know how many terms there are in the series. So since we know a sub 1, which equals 3, I find my r, 6 divided by 3 is 2, 12 divided by 6 is 2, so r equals 2. So that means my last term in the series is 768 equals my first term, 3 times my r, 2 raised to the n minus 1 power. I divide both sides by 3. So 768 divided by 3 gives me 256 equals 2 to the n minus 1. I'm going to take the log of both sides, so log 256. Log of 2n minus 1. So this gives me that. So then I can bring the exponents down front. Divide both sides by log of 2. I'm going to add 1 to both sides. So n equals log 6 divided by log 2 plus 1. So the log 256 divided by the log of 2 gives me 8. So n equals 8 plus 1 equals 9. There are 9 terms in the sequence. Okay, for B, the sum of a geometric sequence is 155. The first term of the series is 5, and the common ratio is 2. So A sub 1 equals 5. S sub n equals 155. R equals 2. Okay, so I have S sub n equals A sub 1 times 1 minus r to the nth over 1 minus r as my formula. So A sub n is 155. Oops. So 155 equals 5 times 1 minus 2 to the nth power divided by 1 minus 2. So this gives me 155 equals it's negative 4 or negative 5 times 1 minus 2 to the nth power divided by negative 1. Okay, multiply both sides by negative 1, so I get negative 155 equals 5 times 1 minus 2 to the nth. Divide both sides by 5. So negative 155 divided by 5 gives me negative 31. 1 minus 2 to the nth. Okay. I'm going to do a little bit of rearranging here. So I have 2 to the nth equals 1 plus 31. So 2 to the nth equals 32. I'm going to take the log of both of these. I can move the n down front. So n equals log of 32 divided by log of 2, which gives me 5. All right, example 6, to use a finite geometric series. Isabel wants to borrow $24,000 for 6 years with an annual interest rate of 4.5% to purchase a share in a food truck business. What will be her monthly payment? So the formula to calculate a monthly payment is A equals P over the sum of K equals 1 to N times of 1 over 1 plus I to the K power, where A is the monthly amount, P is the principal, or the amount that is for the loan, N is the number of months, and I is the monthly interest rate. For Isabella's loan, P equals 24,000, N equals 72, I equals 0.00375. The annual interest rate is 4.5%, so you must divide that by 12 to get the monthly interest rate. Okay. So, and N equals 72 because it was 6 years, and I want to figure out per month. So 6 times 12 gives me the 72. Okay. I substitute the values into the formula, and I saw the denominator is a finite geometric series with A sub 1 approximately 0.996 and R is approximately 0.996. So I find the sum. Okay. So 0.996 times 1.0.996 to the 72 over 1 minus 0.996 is approximately $62.417. So I then calculate the amount of the monthly payment. So 24,000 divided by the 62 is approximately 384.51. So Isabella's monthly payment for the loan would be about $384.51. All right, so what's the monthly payment for a $40,000 loan for 4 years with an annual interest rate of 4.8%? So again, we're looking at monthly for 4 years with an annual interest rate. So my formula is A equals P over sum of K equals 1 to N of 1 over 1 plus I. Okay. So in this rate, so A is the amount that we're paying. P equals 40,000. N equals 4, so 4 times, I'm looking at months, so 4 times 12 gives me 48. And then I is 4.8% divided by 12, or divided by 12, because there's 12 months in a year. So 4.8% divided by 12 is 0.004. Okay. I substitute in these values. I'm going to find the sum first. So the sum where K equals 1 to 48 of 1 over 1 plus, okay, let's see, 1 over 1 plus 0.004 0.004 to the k power. So that equals about 0.996. So equals, when I actually solve for this, 1 divided by 1 plus 0.004, it gives me approximately 0.996. So my rate and my A1 in the series is 0.996. So this equals 0.9996 minus 0.996 to the 48th power divided by 1 minus 0.996. So this is going to equal, this gives me approximately 43.5777. Right, now I'm going to put that back into my original formula. My P is again 40,000, so I'm going to take 40,000 divided by 43.577. Gives me approximately 917.90, or approximately $918. Okay, concept summary, geometric sequences in series. In a geometric sequence, the ratio defined by a term divided by the previous term is a constant, r. Alternately, any term in a geometric sequence multiplied by r gives the next term. So the sequence 1, 5, 25, 125, 6, 25 is a geometric sequence since r equals 5. So in words, each term in the sequence is r times the previous term. The recursive definition gives us, for geometric sequence, a sub n equals a sub 1, where n equals 1, and a sub n minus 1 times r when n is greater than 1. So in our example where r equals 5, I have a sub n equals 1 when n equals 1, and 5 times a sub n minus 1 when n is greater than 1. The fourth term in a sequence is the first term multiplied by 3 common ratios. So the explicit definition is a sub n equals a sub 1 r to the n minus 1. And then my example, again using 5 for r, a sub n equals 1 times 5 to the n minus 1 power. You can find the sum of a certain number of terms in a geometric sequence. For a finite geometric sequence, I have m equals 1 to the n, a sub 1 r m minus 1 equals a sub 1 times 1 minus r to the nth divided by 1 minus r. And the sum of the first 5 terms with r equals 5 is 781. And that is the end of Unit 6, Lesson 7.